Hey everybody, welcome to our second video tutorial for Maple. Again, I created a couple of problems that should be very similar to what you're going to do in your Maple number 2 homework assignment. So hopefully this video will help you be successful with that. If you have any questions or get stuck on anything, as always, don't hesitate to reach out. So the first problem that we're going to start with requires using implicit differentiation and plotting implicit curves. So this relation x cubed plus y cubed equals 6xy, it's not written as a function like f of x equals something only in terms of x's. It's got those x's and y's mixed together, so that's making it implicit. So when we're trying to create an implicit plot as opposed to graphing or plotting just a regular function, we have to do things a little bit differently. So let's make Maple do it. First thing I'm going to do is create a new document, and I am going to upload all of those plots. So we do with parentheses plots, and I'm going to put a colon after it so it doesn't show me all of that stuff after it. All right, now in this first example, we have this curve that we want to graph, and as you can see from some future problems down the line here, we're going to need to take some derivatives and so forth. So in order to not have to retype that equation multiple times, I am going to define this curve here as something, and I'm just going to call it curve. All right, so I'm going to write curve, and then remember how we've done in the past. If you want to define something, you use a colon and then an equal sign. Now, if this was a function, like a function of x, then we would normally put in x, and then we would get that little arrow after it before we type in the rule. But since our problem is not a function, and it's involving both x's and y's, we aren't going to be putting that x with the arrow in it when we create our definition. I'm just going to go straight into typing in the rule. So this rule was x raised to the third plus y raised to the third equals, and then remember, this is asking for 6xy, which is implied to be 6 times x times y. So in Maple, you have to actually manually type in those times, which is really the asterisk key on your computer laptop. So I'm going to do 6 asterisk x asterisk y to get 6 times x times y. So I'm defining this equation to be what I'm calling curve. So if I hit enter, it's now storing it in Maple's memory. Okay, and I wanted to plot this. So again, this is not a normal function, so we're not going to use the normal plot command. Instead, this is an implicit curve, so I need to use something called the implicit plot. So that's just the word implicit followed by the word plot. Okay, and in order to plot this, we are going to do parentheses, and I only have one thing that I want to graph, so I can just go ahead and type it in. And remember, we called it this curve, so I'm going to type in curve, comma, and let's go ahead and tell it what x's, and in this case we also have to tell it what y's we want to use when we're graphing this. What window do we want this to show up in? So I'm going to choose my x's to equal -5 dot dot up to 5, comma, y equals -5 up to 5, and then close parentheses. And there's our graph. Nice little curly Q. Okay, so again, remember you have options here. You could increase the thickness, you could change the colors, you could do whatever you want here. I'm just doing thickness 3 and color red just to show you. Okay, so there's options there, but you don't have to do any of that if you don't want to. All right. So we did part A, we did our implicit plot. The next thing that we want to do is to take a derivative of this. Now, if we were doing this on paper, we would call this process implicit differentiation because, again, the x's and the y's are mixed together. And that's what the command is called in Maple as well. So we're going to do implicit differentiation. And if I type in implicit, and notice as I start to type in the D, you can see this little thing pop up that says implicit diff. And it's like Maple saying, hey, do you mean implicit diff? Is that what you want to do? And yeah, that's what I want to do. But suppose you weren't sure what the commands were that followed it. Maybe you forgot the parameters that you're supposed to type in. Then in front of that word implicit diff, I could put a little question mark. And what this does is it pops up a little kind of tool to remind you what the syntax format should be. So you can see right here at the top, when we enter in our implicit diff, we want to put the function first, comma, and then you're going to use just the plain old y variable, comma, x variable. And that's because, if you scroll down here, it's calculating the derivative of y with respect to x. So whatever derivative variable you're taking with respect to whatever the second variable that you're taking, that's the order that we're going to be putting them inside of these parentheses. Okay, so using that little question mark can be helpful if you've kind of forgotten a little bit about how exactly am I supposed to type this in. So I'm going to remove that question mark, and now after implicit diff, I'm going to do parentheses, and we would want to list the function or whatever it is first. And remember, I have saved this under the name curve. So I'm going to type C-U-R-V-E. And then we want the derivative with respect to y. So do your y first, comma, with respect to x. So put the x second, parentheses, hit enter. So there is our derivative function. Okay, now some of the later questions are going to ask us to do stuff with this derivative. So in order to not have to, again, retype this every single time, let's go ahead and define that to be something. So it's a derivative, and derivatives are slopes. So maybe let's call this slope, and I'm going to define the word slope to be this answer. And the command in Maple to get whatever that last answer was is the percent symbol. So just hit percent, and if you hit enter, it's now defining the word slope to be this derivative expression. Okay? All right, so we have now done part B. Now in part C, we want to find the y coordinate of the points on this curve when x is 3. Okay, so in other words, if you were going to do this by hand, this isn't asking anything about the derivative right now. It's asking what are the y's if you were to let x be 3. So if I was doing this by hand, I would plug in 3 for the x's, but you would still have some y's in there. So you'd have to then solve that equation for y. Okay, so that's what we're going to make Maple do. All right, so anytime you're trying to substitute something into an expression or a function, we can use the command eval. So again, let me do that question mark first so you can kind of see. If I do question mark eval, hit enter, it's going to say this is how you enter in something that you're trying to evaluate. In the first spot, you're typing in whatever the expression is that you're trying to plug into. And then after that, you want to be typing in x equals whatever number you're trying to plug in. Okay? And if we have more than one thing to plug in, then we can use, let's see if there's some examples down here. You can see down here, if you have more than one variable to be plugging in, you can use those brackets and plug them in, like down here. Okay, so let's try this out. We want to, I'm going to take away my question mark. We want to evaluate the original curve. So I'm going to type in the word curve when x is 3. Okay, so we're just substituting 3 into that original function or that original curve. Hit enter. There's the cubic equation that you would get if you plugged in 3 into this curve up here. Well, that's not telling me yet what y is. I would need to finish solving that. So we're going to solve it using the solve command. So I hit or type in the word solve. And then again, make use of that percent symbol. This equation that we have here in this last answer, that's what I want to solve. So I'm going to type in my percent symbol so I don't have to re-type in that cubic equation. And what variable am I solving it in terms of? I'm solving it for y. So I'm going to do comma y. Close the parentheses, hit enter. Now there's your exact solutions. Okay, notice that there's 3 of them. There's the number 3, and then there's this messy guy and this messy guy. Okay, maybe I want to know what those are as decimals. So to do that, we use the evalf command, which evaluates your answers, your last answers, or whatever you're evaluating as a floating decimal. That's what the F stands for. So what do I want to evaluate? I want to evaluate as a decimal these last answers right here. So I'm going to use that percent symbol again, so I don't have to retype in all these messy things, and hit enter. So there's those 3 solutions as decimals. Now, if we look ahead, in problem number D, we're going to basically do what we just did, except we're going to be plugging 3 into our derivative function. Okay, so we'll do that in a minute. And then we're going to be plotting our curves with all these tangent lines. So it might be helpful to know these values and have access to these decimals for some of the work that's coming up later in the problem. So before I lose this information, before I've lost its memory, let's go ahead and define these 3 y values as y1, y2, and y3. So I'll let y1 be defined to be the 3. Okay, so remember, to define something, you use that colon and then equals. So there's my first y value that we got when x was 3. Now let's define y2 to be this negative 4.854101. I won't use all the decimals. Okay, there's my y2. And let's define y3 to be that 1.854101 solution. So those are the 3 y values that you get on this curve when x is 3. So you've got one like right around here, you've got one y value up here, and then you've got another y value down here. Okay, those are the values we just figured out. Okay, so moving on to part D. Now we want to find out what is the derivative when x is 3. Okay, so if we were doing this by hand, we would take our derivative using implicit differentiation, and we would plug in x equals 3, and we would try to figure out what that y value, or what that derivative value is. Okay, so that's what we're going to do, but we're going to make Maple do it. Right? So first thing I'm going to do here is I want to know what the derivative is, and we already did that up here. We defined that to be this slope function. So basically we want to be plugging in 3 into this slope function, and what are we going to be plugging in for the y's? Well, good thing we saved those values. We're going to plug in this y1 value to find the first slope, then we're going to plug in this second y value to find the second slope, and then we're going to plug in this third value to find the third slope. So we're going to have to do this 3 different times. Okay, so here's how that's going to look. We're going to evaluate our slope expression, comma, and here I'm plugging in 2 things. I'm plugging in an x and a y. So I need to use brackets because I've got more than one thing that I'm plugging in. I'm letting the x always be 3. And for the first slope, I'm letting y be that first y value that we solved for, which in this case was also 3. So close the brackets on that after that y1, close the parentheses. Here's the first slope. So what this represents is the slope of the tangent line at 3 comma negative 1. Or excuse me, at 3 comma 3 for that y value, and the slope is negative 1. So visually, if you go to 3 comma 3, which is right about here, and draw that tangent line, that slope is negative 1. That's what we just figured out. Okay, let's call that slope 1. So actually, let's call it m1, so I don't have to type so much. So m1, I'm defining to be that very first slope we got, which was negative 1. Okay, now remember, there's another y value over here with a different tangent line, with a different slope. So let's find that slope next. So to do that, we're going to repeat everything we wrote up here. So eval parentheses slope, but this time still letting x be 3, but now I'm going to let the y value be that y2, because we're looking at a different point on the graph and looking at a different tangent line. So there's the slope of that second tangent line. So let's call that m2. I'm going to define m2 to be that last answer. Okay, now we got one last point to look at. So we're going to do eval slope, comma, bracket. We're still letting x be 3, but this time we're going to let y be y3. So there's the third tangent line slope. Let's call that m3. And I'm going to define m3 to be that value. Okay, so we have 3 points at x equals 3 here, here, and down here, and there's 3 tangent lines with 3 different slopes. So what I want to do for the last question here is I want to plot on this curve all 3 of those tangent lines. Okay, so in order to do that, we're going to be needing to plot the curve along with the tangent line. And for the tangent line equation, I'm going to make Maple do all the work. I'm not going to do any scratch work on the side and then type in that equation of that tangent line. I'm going to make Maple do it. And we're doing an implicit plot because remember, this curve was an implicit function. So here's how this is going to look. We want to do an implicit plot, parentheses, and there's 2 things that I'm plotting. So use a bracket. The first thing I'm plotting is the original curve, comma. The second thing that I want to plot is the equation of that tangent line. So remember, we have point slope formula available to us. If we were going to try to find the equation of a tangent line by ourselves on paper, we would use y minus y1 equals m times x minus x1. And guess what? We know the y1, that was up here. We know the m1, and we know the x1 is 3, because in all of these problems we were looking at what happens when x is 3. So to get the first tangent line, all I have to do is type in that point slope form. Y minus y1 equals m1 times, make sure you put that little dot in between, parentheses, x minus 3. So there's the first tangent line. Now, another comma, and I'm going to type in exactly that same thing again, but this time I'm going to use y2 and m2. So the second tangent line would be at y minus y2 equals m2 times parentheses x minus 3. And then the third tangent line will be y minus y3 equals m3 times parentheses x minus 3. So there's four things going on here. I'm going to close my brackets. I've got the original curve, that curly Q that we had at the very beginning, and then I'm going to draw on top of that those three tangent lines. Now I am going to include some dimensions here. So I'm going to put a comma, and let's let x equal -6 dot dot to 6, comma, let's let y run from -6 dot dot to 6, and then close the parentheses. So let's see what this gives us. There we go. So here's our curly Q. Here's one tangent line at 3, another tangent line at 3, and then another tangent line down here at this 3. All right, and again, you could definitely change some colors here if you like. It's totally up to you. So you could do comma color equals, let's let the original curly Q graph be black, and then the first tangent line will be red, and then the second one will be blue, and the third one will be green. And then you can more clearly see where they are. Okay. All right, so that's all of what's going on in question number 1. Okay, next up. Now we're going to work with an actual function this time. So f of x equals x times square root of 25 minus x squared. And we're going to use Maple to find the critical numbers of that function. Okay, so since I don't want to have to retype this rule every time, let's go ahead and define our function f to be, so f colon equals, and we're defining f to be x, but this time, remember, because we're using a function of x, you need to do that dash or that subtraction symbol followed by the greater than symbol to get that little arrow going first. And after that is when I type in the rule for this function. And this rule was x times, don't forget to put that times in between. And to get a square root, I do SQRT, parentheses. Inside of that square root is 25 minus x squared. Whoops. 25 minus x squared. Close the parentheses. Hit enter. So there's our function defined. Okay, now before I jump in to try to find the critical points, let's go ahead and plot what this graph and also maybe what its derivative might look like. Okay, so just as a review, let's say we plot f, and let's plot it from x equals -6 dot dot up to 6. And I know I'm going to get an error here. I forgot. I need f of x, not just f. Okay. So hit enter. There's our graph. So if we were to just look at this graph, we could predict where there are going to be some critical points. We see a max up here. There's a horizontal tangent line up here. So I'm predicting to have a critical number somewhere over here. And likewise, there's a min down here. So we'll have another critical point as well. So there's probably 2, right? Or there should be 2. Well, let's go ahead and plot f prime of x, comma, x from -6 to 6. And let's see. All right, so this is the graph of f prime. So critical points on the graph of f prime would be the places where the f prime graph is 0, which is right here and right here. So I do see 2 critical points. Okay, so let's find them. Okay, we can see them graphically, but let's actually find their values. So to find critical points, we are trying to find where that derivative is 0. So I would need to solve parentheses where f prime of x equals to 0. So let's hit enter. And there are my 2 values. Okay. Now, those are nice and exact, but maybe we want to know what those are as decimals. So let me do eval f, and I want that last answer converted to decimals. Oops, I forgot the f, sorry. Eval f, actually I'll just fix it up here. I forgot my little f, eval f, and then hit enter. There we go. So we see one of the critical numbers is over here at about negative 3.5, and the other one is at positive 3.5. All right. Okay. So look back here at our problems. We've found all the critical points for f of x. Let's find all the points where the second derivative is 0. Okay, so again, before I actually physically find those, let's look at the plot of f double prime of x. And if I do x from negative 6 up to 6, I'm going to show you something here. Here's what we see. Okay, so when you look at this graph, we have our f double prime, and it is going to have critical points for the second derivative, where this second derivative graph is 0. And the only point on this graph that's hitting at 0 is right at 0. So we can kind of predict that that's going to happen right at 0. So let's solve where f double prime of x, double prime of x equals to 0. Hit enter. I'm getting a couple more values. On my graph, it looks like the second derivative graph is only hitting once, but these two guys are not showing up. So what the heck is going on there? Well, first let's get a sense of the size of those values as decimals. So I'm going to do eval f parentheses. So notice that this guy right here is 6.123, and this one is negative 6.123. So how come they're not showing up on the graph of f double prime of x? Well, let's go back up here for a second. Remember what we defined our initial function to be. It had the square root in it. And square roots can become undefined when the number underneath becomes negative. And if you notice that if we try to plug in a 6 or a negative 6 in for x here, this is going to be something negative underneath that square root. So the domain of this original function f is only the numbers between negative 5 and 5, which you can see from this graph. The graph doesn't go beyond negative 5 or beyond positive 5. So we need to know that we should be disregarding these two solutions because they're not technically in the domain of our original function. Okay, so the only point where the second derivative is 0 is at 0. All right, the last thing we're going to do is we're going to make a plot of f prime, and f double prime all on the same set of axes. So let's do our regular old plot command because we're working with functions here, parentheses, and I'm going to be graphing 3 different things. So in order to plot more than one thing, remember you need brackets. And I want to graph the original function, which I called f of x, comma, then I want to graph its derivative, so f prime of x, comma, then I want to graph its second derivative, so f double prime of x. Remember, you're using the apostrophe key twice there, not the quote key, but the apostrophe twice. Let's close the bracket on that. And since we know what the domain is here, let's let x, instead of going negative 6 to 6, let's go negative 5 to 5. And hit enter. All right, there's our graph. Now just to make it a little bit more clear what's what, let's change the thickness, thickness to 3, and let's change the colors. I've got 3, so I'm going to use a bracket here. Let's let the original function be black. Let's let the first derivative be red, and the second derivative be blue. So there's a nice graph. Here's the original, the black one, where it has maxes. The red graph, which is the derivative graph, has zeros. And where the red graph has a max, the second derivative, the blue graph, has a zero. So that's lining up with what we know about curves and where they have maxes and mins and critical points. Okay? All right, we did everything we needed to do. Hopefully this helps. Remember, you can save your file or you can print off the file, and I would prefer that you print it, print off your work to turn in. All right? Good luck. If you have any questions, don't hesitate to reach out. Take care.